The sequence impulse process or SIP is a novel blast furnace technology that began full operation at Thyssen blast furnace 1 in late 2020. This large 4416 cubic meter furnace operated by Thyssen Steel Europe in Duisburg, Germany has been an impressive operational improvement due to SIP. The technology is now fully incorporated into blast furnace practice and is available to reduce carbon emission incrementally in existing plant. Now coming to the initial investigation and effects, SIP's influence was first tested on one year, comparing with reference years. Observation revealed that 80% of the pulsed oxygen react inside the cockpit behind the raceway. The pulsing effect significantly enhances the chemical conversion of injected coal. Material sampling showed the raceway enlarge reproducibly from about 1.10 meter to 1.50 meter with a pulse oxygen. Now coming to our next slide, which is on the functional principle of SIP. SIP create a supersonic free jet with an unsteady start and a leading shock wave. This supersonic pulse increases turbulence in the raceway, enhancing ignition condition and improving cleaning at the rear of the raceway, which benefit the overall blast furnace process by improving reaction efficiency. Now, as for the plant setup and overview is concerned, oxygen is supplied at a high pressure, as we know, uh, and uh, it is maintaining around 20 bar and above to through the tuyers from the SIP boxes located above the tuyer platform. Each tuyer has a dedicated SIP box that sends oxygen pulses through an injection lance inserted in the blowpipe. Nitrogen is also supplied for the safety and lance cooling. The system creates a shock wave and oxygen pulses, maintaining lance cooling with a continuous basic oxygen flow. Now coming to this illustration of the actual plant, as we can see that above tier platform, all SIP boxes is aligned with the each tier, and these SIP boxes position on a platform as is shown in a figure just above the tier level at the blast furnace, detailing the installation and integration into blast furnace infrastructure. Uh, the additional images and visuals, all these shows the benefits, the information regarding the reduction in the fuel rate, etc., is being shared. So these slides provide images, diagrams illustrating SIP components, the oxygen injection mechanism, and the technology in operation, emphasizing basically the hardware and the raceway condition with and without SIP. So as you can see, there's enlargement in the raceway conditions has been addressed in this slide, and this is how the raceway conditions looks when we have got a pulse in this picture. We have got a eight 2 years which are under a SIP uh, at a common point of time. So this comparison also shows the raceway and the cockpit condition with and without SIP. As the earlier slide gives a lot of information on that. That is when we apply SIP, raceway volume enlarges, and it is getting derived by cleaner cockpit, which enhance the gas flow and chemical reaction. Uh, Coming to our next slide, which is about the technology overview, where SIP uses high pressure oxygen pulses delivered through the specialized boxes at eastway to generate supersonic jets and shock waves. This intensify turbulence, improves coal conversion in the raceway, and promote better gas mixing and mass transfer, mitigating permeability loss and particle deposition. Now coming to our next slide, which is on the operational impact. The SIP process enlarges the raceway and cleans the cockpit, improving permeability and gas flow distribution. Centralized gas flow optimization reduces the wall temperature and the thermal load in the mm, uh, furnace, enhancing cohesive zone performance. SIP also allows increased pulverized coal injection rates while cutting coke consumption, and this in the true sense helps in decarbonization and efficiency benefit. SIP improves thus gas utilization efficiency, leading to a reduction of 50 to 100 kg of CO2 emission per ton of hot metal. The process stabilizes operations even when raw material quality is low, is one of the highlights of this process. Compared to non-SIP blast furnaces, SIP equipped furnaces shows smoother operation, reduced reductant needs, and higher productivity. So operational results as is concerned, we can show that uh, mm, 1.4% increase in gas utilization, uh, efficiency, and significant cost reduction. Uh, Median CO2 emission dropped by 50 to 100 kg per ton of hot metal compared to pre-SIP reference periods. Now coming to the coke consumption reduction, use of SIP enable higher PCI rate, which decrease coke consumption. In a SIP evaluation period, coke replacement ratio exceeded 1.0, meaning coke consumption dropped more than PCI increase. Reference coke consumption was around 530 kg per ton hot metal, dropping to 496 to 509. This is the range during SIP campaigns. Now, as far the gas utilization is concerned, uh, which is defined as CO2 divided by CO plus CO2 increased by 0.6% to 1.4% with SIP. This improvement reduces reliance on the coke and other reducing agent, enhancing blast furnace efficiency. Now coming to the PCI rate uh, increase of the PCI due to SIP allow a substantial decrease in fuel rate. This PCI rate is increasing due to SIP, and this SIP allowed for higher PCI rate and coke. There is a coke rate reduction, and on this cause, on account of this decrease in coke rate, there is a substantial reduction of CO2 also. This is what it's being reproduced in this slide. This CO2, that is reduction summary has been shared, uh, and it already shows that reduction of CO2 emission reduced during SIP campaign by 50 to 100 kg per ton of hot metal due to improved gas utilization or lower overall fuel consumption or optimized thermal loads in the blast furnace. And hence we can say that the uh, operational stability that bring in by this SIP or oxygen pulsing enhances helps, and this is also due to the permeability increase by the enlarging raceway and cleaning the coke bed. This leads to a smoother gas flow and reduced pressure fluctuation and more stable furnace operation. Permeability improvements were quantified by a reduced resistance index indicating better gas flow through the material bed. Coming to the reduced process instability issues like hanging and channeling are also reduced during SIP operation. SIP equipped BF1 experience fewer disruption compared to uh, BF other BF without SIP, especially during the period of poor raw material quality. So, productivity, as far the productivity improvement is concerned, despite poor raw material quality, BF1 with SIP maintain full production capacity, whereas the other PF without SIP struggle and could not exceed even 85%. So SIP enabled higher hot blast flow rates up to 20,000 normal per hour more, which contributed significantly to productivity gains. Similarly, as earlier slide also shows the thermal loads and energy efficiency, and this helps in achieving a better uh, production and productivity data. As for the summary of the advantages of SIP technology is concerned, fuel saving is up to 34 kg per ton hot metal, CO2 emission reduction between 50 to 100 kg per ton, higher productivity even under challenging condition, reduced operational instability such as hanging and channeling, lower thermal loads and extended equipment life, and improved blast furnace adaptability and stabilities are few of the highlights of SIP.